Okay, let's start the week off with some direct variation. This is lesson 2.2, and our objectives are to write direct variation equations, to be able to find the constant of variation, and that's k, and to calculate the ratios between variables, and that will help us to find the constant of variation. Some of the essential understandings for this lesson. Number one, direct variation means that the ratio between two variables is constant. So what does that sound like to you? That sounds like a linear equation, right? Because between any 2 points, if you take y over x, change of y over change of x, rise over run, you would have the same constant ratio. So direct variation is really just a linear equation. Number two, the graph of a direct variation equation is in this form, y equals kx, and you can see it here, right there, where k is the slope. So essentially, it's just like y equals mx, but without a b. Notice that there is no y-intercept. So k, our slope, in a direct variation equation is called the constant of variation, and the y-intercept is 0. If you'll notice up here in this direct variation equation example, the line goes right through the origin, 0, 0. And it is a line, so we know that we have a constant ratio. And you can look and see 4 to 6 is 2, 6 to 8 is 2, and then 8 to 12 is 4, but that's because if you look at what's going on here for x, we skipped 5. Okay, so we went 2, 3, 4. If we had put a 5 in there, we would have a 10 right here. So our ratio is constant. We can tell by the table, we can tell by the line. And we are going through the origin, and that's very important. For something to be direct variation, we cannot have a y-intercept. Okay, in direct variation, x and y vary directly by whatever this ratio k is, that constant of variation. Let's look at some examples. So what we want to know are, do these equations represent direct variation? Well, it's really easy to figure that out. If we just put them in the y equals mx plus b form, we shouldn't see a b, right? All right, once we do that, it says find the constant of variation, and as we just learned, that just means find the slope. So for our first equation, we want to solve for y, so we would divide both sides by 7 in order to move the 7 to the other side. And we would write our new equation. 7 divided by 7 is just 1. Right, so those are gone, and we're left with 1 equals 2 over 7 times x. Well, I don't see a y-intercept on the end, right? We have plus 0, so this one is definitely, yes, this is direct variation. All right, so part 2 says, find the constant of variation. Well, that's pretty easy to do as well. The constant of variation, that's our k, is in fact 2/7, right? Because remember that k is just our slope, or m, but in this case, since we're doing direct variation, we call that k. All right, moving over to the next one. In the second one, we have to determine once again if it is direct variation by turning this into y equals mx plus b form. So if we subtract 4x from both sides in order to isolate y, see what we have. We have bring the 3y down. We didn't do anything to that. 4 minus 4 is 0, so that's gone. 8 minus 4x, we can't combine those are not like terms. So we have a minus 4x plus 8. And I went ahead and put the one with the x first, just as in our y equals mx plus b. Now we need to move the 3 over, so we need to do the opposite. So we need to divide everything by 3. Well, 3 divided by 3 turns into 1. So we get y equals negative 4 over 3x plus 8/3. So you can see right away, is this direct variation? This one is not direct variation. And our reasoning is because it does not go through the point 0, 0, right? This y-intercept throws off the ability of x and y to vary directly by our slope or our constant of variation. So we would say this is not direct variation. All right, let's look at a couple other things. Let's move on to the next slide. We want to write a direct variation equation. So to write a direct variation equation, we first need to find the constant of variation k, otherwise known as our slope. And we can do that using an ordered pair that you know is part of our graph. That is the solution to the problem. It falls on the line. So if, for example, I were to go back to this first slide, any one of these points here or on here, those points are all solutions to this line, right? They were all on the line. So I can choose any 2 points that are on the line, and that's what that means. So suppose y varies directly with x. So right there we know this is a direct variation equation just because of this statement, y varies directly with x, meaning we do not have a y-intercept in there to stop that. And then it tells us that y equals 35 when x equals 5. Essentially what they're telling you is they're giving you a point, and y equals 12 here when x equals 6, and y equals 8 here when x equals 4. So all they're really doing here is giving us a set of points. Then it says what direct variation equation relates x and y, meaning we need to write a direct variation equation given these points. Actually, this is 1 point, right? What is the value of y when x equals 9? So that's a second thing that we will do after we have found the direct variation equation. So first things first, we would start with the function form of a direct variation, y equals kx, or as you know, y equals mx. But remember, we're using k now. Second thing is to substitute the 5 up here in for x, right, when x equals 5, and the 35 in for y here because it tells us y equals 35. So look what I have. I have an equation with only one variable k. Surely I can solve for k. If I divide each side by 5, I get 7. K is 7. That is my constant of variation. And that's all I need in order to write a constant of variation equation in this form here, y equals kx. I know k. So let's write it in. We'll substitute the 7 in for k, and we have y equals 7x. Okay, so that brings us to our last question. What is the value of y when x equals 9? So once you have an equation, then you can start answering questions like that. If I come back to this graph, and on our first slide, if I said, okay, what is the value of y when x equals 4? Well, you can say, oh, when x equals 4, the value of y is 8 right here in the table. Or you can go to the graph and say, well, here's 4, and now if I go over, you know, there's 8. Okay, so wherever that is. So it's easy to look at a graph or a table, or in this case, what we're about to do is we can use the equation. So if we know x, we could substitute the 9 in here for x, and that would give us y. So the equation y equals 7x relates x and y. When x equals 9, y equals 7 times 9, or 63. So really, this is a two-part question. We need to have first written a direct variation equation based on this point, and then we need to find the value of y when x equals 9. Let's try some on your own. So go ahead and pause the video and give these a try, and then come back and let's do them together. Okay, so hopefully you have something written down. Suppose y varies directly with x. So again, direct variation equation, and I'll go ahead and write this form in the form of y equals kx. Okay. These are really easier than linear equations because you don't have to mess with the y-intercept. So all you need is 1 point to figure out your k. And then it says y equals -18 when x equals 3. So that's code for, let's plug those into our equation. Well, y equals negative 18. We don't know k, but we do know x, they say, is 3. What direct variation equation relates x and y? Well, first things first, I need to solve for k, so I'm going to divide both sides by 3. And I would get negative 6 for k. So if I'm writing my direct variation equation from all this, I would get y equals negative 6x. Really nice and simple. I have nothing over here, and there's my equation. Now I can do part 2, which says what is the value of y when x is 12? All right, so using this same equation, I have my y, and I have my constant of variation. I'll plug in a 12 for x and solve for y. So y is going to be equal to negative 6 times 12. 6 times 2 is 12, carry the 1. 6 times 1 plus 1, that would be 6 plus 1 is 7. So there's our second answer, negative 72. All right, moving on to the second problem. Again, suppose y varies directly with x. We know right away that's going to be in this form, y equals kx, direct variation equation. And it says, and y equals 4 when x equals 20. So again, what that means is, well, let's make y equal 4. We don't know k. And let's make x equal 20 because they tell us that. What direct variation equation relates x and y? Well, in order to write a direct variation equation, I need k. So let's go ahead and get k. Let's divide both sides by 20. Now, 4 goes into itself once. 4 goes into 20 5 times, so I just reduced that fraction. And 20 divided by 20 is 1, so I'm left with k. All right, now I can write a direct variation equation based on this information. My direct variation equation is going to be y equals 1/5 x. And I'm done. Let's now look at part 2. What is the value of y when x is 7? Okay, so what is y? Here is my constant of variation. And it says when x is 7, so I can plug in a 7 for x. Well, y is going to be equal to 1/5 times 7. Remember that 7 is like 7 over 1. So 7 times 1 is 7, and 5 times 1 is 5. And that's the answer. Okay, so very simple. Let's wrap this up by looking at a contextual example using direct variation. A lot of things vary directly without an initial amount. So that would be like the weight on Mars. So weight on Mars represents our y, varies directly with the weight on Earth, which is represented by x. And so here's some science, some weights, I guess, of these science instruments aboard the Phoenix Mars lander. So the weight on Mars was 50 pounds, and that same instrument, the weight on Earth, is 130. Okay, and let's mark what we have. Problem says the weight on Mars is represented by y, so this is y. The weight on x is, the weight on Earth, sorry, is represented by x, so that's x. What is an equation that relates weight in pounds on Earth, x, and weight on Mars, y? Okay, this is just like the other one, right? X is this amount, y is this amount. We can create an equation, a constant of variation equation, y equals kx, by substituting the x and y values that we know. So the y is 50. You're 50 pounds on Mars. We don't know the constant of variation. We're about to find it. When the weight on Earth of the same instruments is 130. So let's find our constant of variation. So we're going to divide both sides by 130. Okay, now when we're doing our constant of variation, it's helpful to have a number in this case because this is a real world example. Okay, well 130 divided by 130 is gone, so our constant of variation is going to be equal to whatever 50 divided by 130 is. So we'll pull out the calculator and we'll do that math. 50 divided by 130 gives us 0.38. So I'm just going to round 0.38. The next number is 4, and since that's less than 5, I don't need to round up. All right, now I can do my final step, and that is to write a direct variation equation using that. So y is equal to 0.38, oops, there's an 8x. Okay, now let's look at part 2. So the equation y equals 0.38x that we found gives the weight y on Mars in pounds of an object that weighs x pounds on Earth, right? Mars and Earth vary directly by this constant of variation, 0.38. What we want to do first is graph the equation relating the weight on Earth to the weight on Mars. So one way we can do that is to make a table of values, plot the points, and draw a line. And we know, if you look at the line, that we should be here at our y-intercept of 0, 0. So the first point that I chose was 0 for x. And if I plug it in, well, 0.38 times 0 gives us 0. Okay, then I chose 50. You know, why would we go up by 1 and 2 and 3? Because who weighs 1 pound and 2 pounds and 3 pounds? Or what type of equipment do we have that only goes up that small? So let's go with bigger increments like 50, 100, 150. And plus we have a really tiny number here, right? That's less than 1. So we don't want to get a bunch of decimals, so I chose 50. And 50 times 0.38 gives us 19, right? The 50 gets plugged in here for the x value. Then I chose 100. 100 times 0.38 is 38, and then I chose 150. 150 times 0.38 is 57. So now I can plot these points. Right here is my 0, 0. Then I go 50, 19 is about here. And then 100, 38 is about here. And 150, 37 is here. Notice the points form a linear pattern. We would draw a line through them. And we have now graphed the relationship between the weight on Mars to the weight on Earth. So let's answer these questions. Try to answer these on your own first. What is the slope of the equation y equals 0.38x? Okay, well, as we've been talking, the slope is just the constant of variation, which is 0.38. What will you weigh on Mars if you weigh 125 pounds on Earth? There's multiple ways to figure that out. We can do it like the table. We can put an x value of 125, plug that in. 125 times 0.38 will give us a number. Or because we've spent so much time graphing, let's just look at the graph. So I'll go over here to 125, and then I'll go up here, find that point, and that looks like it's about, and this is approximate, because I didn't do an actual calculation, but it is approximately, we'll say 48. And that's close enough, right? It could be 47, it could be 49, but we know it's a little bit less than 50, but almost 50. Okay, and on our final slide, what we're going to do is look at an example from a table. So for the data in the table, does y vary directly with x? If it does, write an equation for the direct variation. So here's something where it's not telling you that it's a direct variation, but you have to determine if it is. So the way to do it is we need to find the change in y. So we're getting 6 here. We are getting 3 here. So on first glance you would say no, but notice how our x's are not going up by a constant amount. So let's look at the change in x. 4 to 8 is 4, and 8 to 10 is 2. So since these aren't going up by a constant amount and these aren't going up by a constant amount, let's create some ratios. Okay, so for our first ratio, and remember it's always y over x, so if we did 6 divided by 4 in order to get our ratio, well, 6 divided by 4, we can reduce that to 3 halves, and 3 halves is about 1.5. Let's look at our next point. Okay, and remember, really all we're doing is we are looking at constant variations for each of these. And if I go back to some examples, just to help you, Notice that every time what I end up doing is taking my y value 18 and dividing it by my x value here, which is 3, to get my constant of variation. I did it down here as well. I took my y value, which was 4, and I divided it by my x value here, which was 20. So we're taking a little shortcut. We're not writing an equation. We're just dividing these out to see if they're all about the same. Okay, if I'm going to reduce this, I would get 3/2, which is also 1.5. So right now I have a good suspicion that I have a constant ratio from point to point. We can try the last point. 10 over 15 reduces to, oops, now see I'm backwards. Be very careful about that. You have to do y over x and be consistent about that. It's always rise over run. So 15 over 10 gives us 3/2, which is the same, 1.5. The nice thing about doing this is now I know what my k value is. I know my constant of variation. So this one does have direct variation, and we can write an equation which is going to be y equals 1.5x. All right, let's look at the last example of the lesson. So again, let's see now if we notice that these, let's check how these go up. So this goes up by 3, -2 to 1. This goes up by 3, so it's actually going up by a constant amount. So as long as these two go up by a constant amount, we would have direct variation. Okay, so it's dropping down. Looks like it's going down by 0.8. And then this one is going down by, also looks like it might be 0.8. Okay, so I think that this one is also probably direct variation, but let's do our test like we did last time. So we have our y, 3.2, divided by -2, so that would give us -1.6, and then we have 2.4 divided by 1, so that is actually giving us just 2.4. And our last one, 1.6 divided by 4, gives us 0.4. So if you'll notice here, we do not have a constant ratio, so we have to be careful. Even though this is going up by a constant amount and this is going up or down by a constant amount, the problem is the ratio between the two is not constant, and that's what we care about, the ratio between the y and the x. And since it's changing every time, we would say that in this problem, this is not direct variation and we cannot create an equation. And that concludes our lesson. So make sure you go back and review if you need to. Understand that direct variation, the key thing with that compared to a linear equation is that there is no y-intercept. X and y vary directly by the slope, and in this case we call it k, or the constant of variation.